Welcome back. Today we're going to learn a new rule of differentiation called the chain rule, and it's going to help us differentiate functions like the one we have here, y equals the square root of x squared plus 1. Now, this is not a function that we know how to differentiate yet. We don't have a rule that will help us differentiate this. And the reason is because this is a little bit more of a complicated function that we've dealt with before, specifically in that it is a composition of two different types of functions. Here, if we look at this square root, on the inside, we have x squared plus 1, and you could look at that as a function of x. It's a polynomial function in particular. And then we're taking that polynomial function and we're taking the square root of it. So there's two functions that are kind of acting on x. The inside function is a polynomial. We've got x squared plus 1. That itself is a function of x. But then we're taking that and we're taking the square root of that. So this, what we have right here, this is a composition of functions. And there's a rule called the chain rule that we're going to be able to use when we're dealing with a composition of functions. Now, what I want to do, I'm going to tell you the chain rule in just a minute, but I said that there was kind of an outer function and an inner function. The outer function is that square root. The inner function is the x squared plus 1. I want to make a substitution just to make the thing look a little bit simpler. What we're going to do is we're going to let that inner function be equal to u. Let's let u be x squared plus 1. If we do that, then what we can do is we can write this as y equals the square root of u. And by doing this, we're kind of actually separating those outer and inner functions. We've got x squared plus 1 is the inner function, and then the square root of u is the outer function. And we know how to differentiate both of these types of functions. We've differentiated the square root of x before. I know it's u here, but we've differentiated this. This is a power function. We've also differentiated polynomials before. So in particular, when we let u equal the inner function, we can see that we can differentiate the outer function and we can differentiate the inner function. So those two functions we already know how to differentiate. The question is, how do we manage when we're dealing with a composition of these two functions? And I'm going to write out the chain rule, and there's different ways of writing it based on the different types of notation. I'm going to start with the one that, for me, is the most intuitive. In this original function, we want to differentiate y with respect to x, right? X is the independent variable that we're differentiating with respect to. So what we want is dy over dx. We want the derivative of y with respect to x. And what the chain rule says is if we want to differentiate y with respect to x, and we have a composition of functions here where we can write y as a function of u and then u as a function of x, the chain rule says that dy over dx is equal to dy over du times du over dx. Meaning we can differentiate y with respect to u, and then we can differentiate u with respect to x and multiply those things together. Now, I don't want you to think that these are fractions and we can cancel out du, right? These are not actually fractions. These are ways of writing that we are differentiating one quantity with respect to a different variable. So we cannot just cancel these as though they are factors in the numerator and denominator of a fraction. That's not how it works. That's not why this is the chain rule. But as long as we recognize that, we can look at this, and it does intuitively if they were fractions, it would look like it would make sense. And so at the very least, we can kind of use that to help us remember this rule. Now, what I want to do is I want to go through this example so we can see how it works. And then I'm going to write out the chain rule a little bit more formally with kind of different types of notation so we can see that. And then we're going to look at a couple more examples. So let's look at this. We want the derivative of y with respect to x here. And I've said that this is the same as dy over du times du over dx. Now let's actually put out what these derivatives are. We need the derivative of y with respect to u. Now y is the square root of u, which we know is the same as u to the 1/2 power. And the derivative of u to the 1/2 power is 1/2 u to the negative 1/2, using the power rule. So that is the derivative of y with respect to u. And then we need to multiply by the derivative of u with respect to x. Well, u is x squared plus 1. The derivative of that is just going to be 2x. All right. Now, there's a couple of things we need to do. We wanted the derivative in terms of x, so we cannot leave the u in the answer. We need to go back and replace u with whatever it is in terms of x. But also, there's some algebraic things we can do here. First of all, we can cancel out the 1/2 and the 2, because 1/2 times 2 is just 1. And then we know that if we raise something to the negative 1/2 power, the negative moves it to the denominator, and the 1/2 power is the same as the square root. So we can also write this as x over the square root of u. Right, we've got the x that stays where it is, and then this part goes in the denominator as the square root of u. And then we just have to substitute back in for u in terms of x. We know that u is x squared plus 1. So down here, when we have the square root of u, that's going to be the square root of x squared plus 1. And this is the derivative of y in terms of x. All right, now that we've gone through an example, I want to give you the chain rule written out in a little bit more of a formal way. We have the chain rule, and it says that if we have a function, capital F of x, and it's written as a composition of functions where the outer function is lowercase f and the inner function is lowercase g, so we've got a composition of functions that we want to differentiate. The derivative of that composition is going to be the derivative of the outer function evaluated at the inner function. That's just basically what we did here, where we plugged the inner function back in for u. So the derivative of the outer function evaluated at what's inside times the derivative of the inner function. It's basically the same thing that we just saw. Here, y is a composition of functions where the outer function was the square root and the inner function was this u, x squared plus 1. And to take the derivative, we took the derivative of the outer function. That was the derivative of the square root of u. That's where we got this here. And we're evaluating it at the inner function. That's why we plug in the x squared plus 1. Times the derivative of the inner function. That's where we differentiated the x squared plus 1. Again, the first time you see this, the notation's going to be a little intimidating. But really, all we're doing when we've got this composition is we're differentiating the outer function and differentiating the inner function and multiplying them together. I want to look at two similar but different examples so we can get a little bit more comfort here. Let's differentiate y equals sine of x squared and y equals sine squared of x. All right. Both of these are compositions of functions that involve sine and also squaring, but the order of the composition here is a little bit different. In this first function, the inner function is squaring, and then the outer function is taking sine. But in this one, the inner function is sine, and once we've taken the sine, we end up squaring things. Remember, this is the same as sine of x quantity squared. So here the inner function is sine and the outer function is squared. Let's go through and differentiate both of these. We're going to start with y equals sine of x squared. Let's let the inner function be u. So u is our x squared. And if we do that, then we can think of y as sine of u. And our chain rule says that if we want to differentiate y with respect to x, we've got to take dy du times du dx. All right? Now when we do this, we need the derivative of y with respect to u. Well, if y is sine u, do you remember the derivative of sine? It is cosine. So we've got cosine of u times the derivative of u with respect to x. Well, if u is x squared, then the derivative of that is going to be 2x. But remember, we can't leave a u in our answer because we want the derivative in terms of x. So we've got to go and back substitute. U was x squared. So this is actually going to be cosine of x squared times 2x. And we usually put coefficients out front. I think it looks nicest if we write 2x cosine of x squared. Either way, though, we have our derivative. All right? You don't actually have to write out all of this. We can remember that the chain rule says when we're differentiating a composition, we take the derivative of the outer function, evaluated at the inner, times the derivative of the inner. The outer function here is sine. The derivative of sine is cosine, evaluated at x squared, times the derivative of the inside. The derivative of x squared is 2x. So we can jump all the way to here once we're comfortable with this rule, right? The derivative of the outer function, derivative of sine is cosine at x squared, times the derivative of the inside, derivative of x squared is 2x. Let's take a look at this other one. It's the same two functions, but the composition works differently here. So here the inner function is sine of x. So we can let u be equal to sine of x. And then in that case, y is equal to u squared. So again, our dy over dx we get by taking dy over du times du over dx. So the derivative of y with respect to u, what's the derivative of u squared? 2u times the derivative of u with respect to x. Well, the derivative of sine of x with respect to x is cosine of x. So this is going to be times cosine of x. But remember, we want everything in terms of x, so we've got to back substitute in. U was sine of x. So here we have 2 times sine of x times cosine of x. And if you remember your trigonometric identities, we can also write this as sine of 2x. All right. But again, just the fast way of doing this, remember we take the derivative of the outer function, evaluated at the inside, times the derivative of the inner function. If we look here, the outer function is something squared, u squared. So the derivative of that is 2u, 2 times sine, times the derivative of the inside. The derivative of sine is cosine. So that gives us 2 sine x cosine of x without having to write all of this out. But again, that's once we start getting really comfortable with the chain rule. Now, the chain rule is a very, very important rule of differentiation because we need it any time we have a composition of different types of functions. This is going to end up being your bread and butter. You want to get super comfortable with this. So I've got lots of videos of worked out examples, and I really want you to go through them, try them on your own, and then watch the video afterwards to see if you've been doing them right. Get more and more practice to the point where you can do these without having to write out the whole let u equal blah, blah, blah. Because eventually, and eventually is the very next lesson, we want to look at situations where we have compositions of three functions, where y is a function of u is a function of v, and then v is a function of x. And we want to be able to do this triple style. So you've got to make this a priority. You've got to make sure you really get this thoroughly.